Hi there. This video is about projectile motion. Now, projectile motion is any motion where the object is only interacting with the earth, so it's only feeling gravity. The only acceleration, the only force on it is the force of gravity, the acceleration of gravity. So we've already been doing this. So basic dropping or throwing straight up, those are projectile motion. But typically when we talk about projectile motion, we're talking about something a little more interesting, which is two-dimensional kinematics, two-dimensional motion. So whee, something like that. So when we have something moving in both the horizontal and the vertical directions, that's typically what we're talking about with projectile motion. So the demos that you predicted and looked at should have given you the idea that for projectile motion, the vertical and the horizontal are independent of each other. What happens in the up-down, it has nothing to do with what happens left-right. And we saw that because the drop-shoot experiment, so it takes the same amount of time for something to just drop as it is to be fired horizontally from that same height. So the horizontal component doesn't affect the vertical. It takes the same amount of time to fall from here to here, whether it's moving horizontally or not. So independence of motion, independence of the two directions is the key. It is absolutely the key for projectile motion. We're going to be focusing on two types of projectile motion. We're going to be looking at horizontally launched objects, so a horizontal launch, and then we're going to be looking at things with an angled launch. So something that's launched horizontally would be something like this, where I just fire something, whoop, 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 and it falls. But it's initially just whoop, right horizontal, like that. Angled launch is the more traditional, you think of like a baseball or a football or something like that. So those are the two types that we're going to be focusing on. With both of these, that independence of motion idea is something that you should be able to start after a while at least, you should be able to start thinking about as, okay, so X, horizontal, and Y are independent. So for something like this, the horizontal movement, imagine, so let's say this is a baseball home run, okay, so it's flying through the air. And if you imagine yourself in a blimp above the baseball field, looking down, all you would see is, you wouldn't be able to tell from that high up if it's going up and down. All you'd see is this motion like this. Similarly, the vertical motion is like the umpire, an umpire with no depth perception. How about that? So if you have an umpire looking, at the ball leaving the home plate, and it's going up and it's going away, but he can't tell, or he can't tell that it's going away. All the umpire sees is it goes up and then it goes down. That's the idea of the independence of motion. All we care about is, okay, it's going to go up and down, or it's just going to go sideways. Visually, we put those together into this. But for figuring this out, for solving the physics of it, thinking about the physics of it, we take them separate. We take horizontal and vertical totally separately. So with the horizontal launch, let's start with that one. If we're going to launch something horizontally, so, and it's going to go like that. So that's just our basic condition. What is special about this? Horizontal launch is usually simpler than an angled launch. Well, usually it is. It just is. Why is it simpler? What's special about a horizontal launch? Well, let's think about the variables that we've been dealing with. So here are the 6 kinematics variables that we've been dealing with. Now we're going to take the vertical and the horizontal as separate, which means that now we need to think about this in terms of horizontal and vertical. So we actually have 6 times 2, 12 kinematics variables. And we're going to have to start using some subscripts because got to keep these straight. This has nothing to do with this, except that the time is the same. So there's a divider line here. You can't do both. So what's special about a horizontal launch that would make it easier? Well, okay, we're distinguishing horizontal from angle. There's something about direction, clearly. We have an initial velocity going this way, horizontally. All right, so horizontal initial velocity. Okay, so initial velocity is these two pieces right here. The initial velocity horizontally in the x direction and initial velocity vertically. What's true in the horizontal case? Well, all of the initial velocity is horizontal. So all of that initial velocity is Vix. That means there's no up and down component at the start. So when it just gets fired off, there's no up-down portion to it, which means that the initial vertical velocity is 0. And this is always true for a horizontal launch. It's something special. And that 0 right there, that makes the math easier, which is why horizontal launches are easier than angled launches. Okay, now let's focus on an angled launch. For an angled launch, that's something like, that baseball home run. So it's launched at an angle. It starts moving with some initial velocity like this. And it's going to go down. It might start above ground. It might start on the ground. But let's just focus on this initial piece right here. What is true about the initial velocity? All right, so it's going up and to the right. So let's say it's moving at 5 meters per second. Okay. Well, where does that 5 meters per second fit into here? We don't have this anymore. Okay, so we don't have that. Is this 5? Is this 5? I want you to stop and think about that and say, do you think that both of these are 5? Is one of these 5, or are neither of them? So stop, think about it, make a prediction. Okay. What did you guess? What did you think about? Well, I'm going to think about this in the sense of, again, independence of motion, of the two motions. So if I think about the horizontal component and I think about the vertical component, those are totally separate from each other. Well, this isn't horizontal or vertical, it's both. So how do we handle that? Well, this is why we did the vector review. This is why we had you check up on your vectors and how to find the vector components. We need to break this 5 meters per second up into its components. So, when we have a vector, 5 meters per second, let's just say it's at 15 degrees above horizontal. This is definitely the initial velocity, but that is not the initial velocity in the x direction. It's not the initial velocity in the y direction. Neither of those are 5. And if you think about what the triangle rules must be, if the long side is 5, both of these must be smaller than 5. This isn't 5, this isn't 5, they're both smaller than 5. So how do we figure out what those are? How do we do that? That's our vector components. So this is initial velocity in the x direction, that's our horizontal component. This is initial velocity in the y direction, our vertical component. And, well, let's just start with, I don't know, one of the components. Which one? I don't know. X? Sure. Okay. So what is Vix? What is the initial velocity in the x direction? Well, we know the hypotenuse, we know the angle, and we're looking for this side right here. That is adjacent to the angle. If you remember SOHCAHTOA, what has adjacent and hypotenuse? SOHCAHTOA, ka. So I'm going to say, well, the cosine of 15. Cosine is adjacent, Vix, over hypotenuse, Vi. If I just bring this up to the other side, well, that means that the initial velocity in the x direction is the initial velocity times the cosine of the angle, 15 in this case. This right here, you're going to be doing over and over and over throughout most of the class. You're going to have to break up in these forces or velocities, break up these vectors into the components. So get comfortable with saying, okay, this is the adjacent side, that's the cosine side. Similarly, if we do the sine of 15, Sine is opposite over adjacent. Opposite, VIY. I'm sorry, I misspoke. Opposite over hypotenuse over VI. So the initial velocity in the y direction is the initial velocity times the sine of the angle. So these two right here you're going to be seeing a lot. Get in the habit of saying it's the adjacent side, it's the cosine piece. This is the opposite side, it's the sine piece. So when we have problems with angled launches, the first thing you're probably going to want to do is say, oh, I got to break that angle up into its components. I can't use the initial speed. I can't use that because it's not in x, it's not in y, it's both. So I got to split them up. Say they're independent, I got to deal just with VIX or just with VIY. So that's some of the basics of the projectile motion, both horizontally launched. And horizontal launch, you always know that the initial velocity in the y direction is 0. And then with the angled launch, you have to take VI, the initial speed, the initial velocity, and break it up into VIX and VIY. All right, I think that's all for projectile motion. I hope this was a good introduction and that those demos that you saw will start to make sense as we go through more of the concepts and start doing practice problems in projectile motion. Good job.